Okay, so and I keep getting myself just a little ahead. This is not quite where we were. Let's see. Okay, we were about right here. Right, so the last thing we did was this example where we were able to compute the area of a sphere by adding up a bunch of areas over the surface. And the big idea was, kind of inadvertently, we found ourselves having computed this stretching factor. It's effectively a stretching factor between parameter space area and surface area. And with that formula in mind and computed, in the case of this sphere, we were able to compute the surface area of a sphere. So that's nice. Now that's about where we left off last time. And this next little bit here is really just a summary of stuff we've already talked about. But I guess that's a nice way to start the class. So remember, we have a parameterized surface. Remember that means that position is a function of the two input parameters s and t. So that defines for us this surface here. And various computations you can do on this parameterization. You can compute its various partials, which end up being velocities of the coordinate curves. And that allows you to compute then these little displacement vectors, which allows you to compute this area ds, which we just got through talking about. It also, along the way, we computed this thing called capital N, which is going to come up in multiple places going forward. Or right now, it's just the thing, magnitude is the stretching factor. But it will be more than that. Okay, and so then different ways that you can write this. In particular, I want to point out that this formula where we cross these two partial, I guess you could call these partial velocities. Right? If you just write them out in coordinates and actually crank out that cross product, what you find is that each of the coordinates of that cross product, in a seemingly really weird coincidence, are two-dimensional stretching factors. They have exactly the same form as two-dimensional area stretching factors, like from change of variables. And that does seem like a coincidence. It's not. As it turns out, there's a really good reason for this, and if we had more time in this course, then I would surely use some of that time to talk about why this is not a coincidence and how this is actually a really neat observation. We're going to scratch the surface of it a little bit later. But for this course and for now, I'm just going to say it is what it is. And you might say it's a nice little memory tool, perhaps. Anyway. Okay. All right. Now, I want to bring your attention to a special case. There's a particularly nice special case. Namely, what happens to the above formula when you are using a graph parameterization. Remember, lots of parameterizations are graph parameterizations, specifically where you can solve for one of the variables then as a function of the other two. And here's the thing. That means your parameterization will always be of this form, which means that your partial velocities will always be of exactly this form. Which, if you cross with each other, you will find that your capital N vector is always of this form, which means that your stretching factor, your area stretching factor, will always be of this form. That's a really nice little fact to remember. Whatever function it is that you're taking the graph of to define your surface, plug it into this formula right here, boom. There's your stretching factor. It saves you a little bit of effort in writing down these partial vectors and in writing down the cross product, having to compute the cross product, etc. Now, it's not a tremendous amount of effort, but it is a little something, and it is therefore, I think, a reasonably worthwhile thing. So I encourage everybody to memorize this formula. It's not required in the sense that you could just go through the algorithm, which, of course, you definitely have to know. What I want to warn y'all off of is the idea that you could know this formula instead of the more general formula. And that is absolutely not the case. This formula right here is supplemental only, right? It only applies to graphs. And well, yeah, sure, there's a lot of there are a lot of parameterizations that are graph parameterizations. There are a lot that aren't, right? And for those that are not graphs, you cannot use this. It doesn't make any sense. There's no way to make use of this formula. So supplemental only. Okay. But it's a nice supplement. Now that said, cool observation. This part right here, magnitude squared of the gradient. Easy observation. You just kind of notice, in fact. Next observation I'm going to make. The magnitude of the gradient is the steepness of the graph. Right? So this then is a different way of saying that same thing, that your stretching factor can be rewritten in terms of steepness. And if it should come to pass, as in the example I'm about to show you, where you know the steepness, maybe the gradient's a little harder to talk about, but if you know what the steepness is, then you can plug that right in to this formula. So here's the example I'm going to show you. And by the way, this comes out of a real life experience that I had when I was let's say a kid, a little older than that, I guess. But anyway, this concerns the roof of a house. Here's my best shot at drawing the sort of the structure of a house. I hope that looks vaguely house-like. And you can see in particular the roof, and of course the roof is made up of several faces. Not every roof is different, of course, and so but on this house, and a lot of houses anyway, there's a bunch of different faces that look like this. Let's ask the question, how would I compute the area of this roof? Now, if you don't know any multivariable calculus, then you would look at this and think, all right, well, step one, I'm going to have to figure out the area of this triangle. It's not a right triangle, right? And so, I guess you could... There's formulas, right? There's ways that you can do that, but this is not a particularly convenient way to compute. And then, of course, there's lots of other faces, each with its own challenges. So here's the clever observation. Clever observation is this graph overall, right? The roof itself overall is, I said that backwards. The roof overall is a graph. Trying to find the area of a graph, we can write with this formula right here that we just talked about. And here's a little architectural point. All exceptions granted, but surprisingly often, the steepness on a roof is approximately constant. It's as close to constant as they can make it. And I couldn't tell you exactly why that is, but my understanding is this is a surprisingly common thing. This is, I don't want to say always, again, architects are very creative and they come up with all sorts of cool looking things, gables and stuff like that. But in a lot of houses, that steepness is approximately constant. So here's the thing. If that steepness is approximately constant, then that means that this whole expression here on the inside is constant, and constants factor right outside of the integral. And this is a massive simplification because if you look at what remains then, having factored that out, what remains is just the area of the footprint. And the area of a footprint, this is a bunch of rectangles. That's easy. Tape measure and a 2-function calculator, and boom, you can compute that effortlessly. Right? So this turns several non-trivial calculations into kind of one easy calculation and then multiply by a little magic factor. So nice little example. Now, why would we care about this? Who cares about the area of a roof? If you ever own a home someday, you might probably have to actually pay to get someone to put a new roof on your home. And shingles are shockingly expensive, as in many thousands of dollars for a roof's worth of shingles, right? $10,000, $15,000, it's a lot of money, right? And knowing exactly how much area there is up there so that you can make sure that you're not paying more for your shingles than you should is worth a little back of the envelope computation such as this one. So, okay. All right. Questions? Yeah.
What's the footprint area?
Yeah, so the footprint area is, this is what I'm calling the footprint of this is, when you think of the integral as happening over, dx dy, this is what you might call the domain of that integral. So this is the pullback domain when you're doing the graph parameterization. Yeah. Okay. So we're going to take the ideas that we've just talked about and just kind of generalize them a little bit. Suppose we want to do some sort of whole is the sum of the parts, chop it up, add it up, however you want to say it. Not on an area in the plane, not on a three-dimensional solid, not on a curve in space, but rather on a surface in space. We haven't ever talked about this before. So we need to make up a brand new kind of an integral. I do want to point out, though, that this is not entirely unfamiliar territory. Let's look back here at Chapter 6 when we defined scalar line integral. Right? And notice the big idea of, if you have a new kind of a domain, right, is to make a formula for a Riemann sum, the idea of which is that on each little piece, the problem becomes easy, right? If you're doing a scalar line integral, on this little piece of length delta s, whatever it is that we're computing can be thought of as quantity per unit length times length. And on this little piece, that's an easy question because everything's approximately constant. And it's just, an easy question on that. So a hard question is the sum of a bunch of easy questions. So this is just the usual Riemann sum strategy for addressing an accumulating quantity, right? And we're going to do morally the exact same thing here. I have a whole that I can chop up into a bunch of little pieces. On each little piece, now we gotta slow it down a little bit. This isn't exactly like a curve, right? After all, this is a surface, little pieces of which don't have lengths, they have areas. And so on that little piece, if I want to know how much mass there is on this piece or how many ants are crawling around inside of this little piece of my surface, whatever the question may be, quantity per unit size times size will give me quantity. In this case, quantity per unit area times area. Right? So this suggests, I'll say it this way. This is a new kind of a Riemann sum. We can call this an integral on the surface. And the notation, as usual, I think is pretty easy to motivate. And we end up with this shorthand notation representing this new kind of an integral, this surface Riemann sum that we more commonly refer to as a scalar surface integral. Okay, now again, why the term scalar? Well, don't forget when we were talking about line integrals, we called this a scalar line integral because the differential is a scalar and the integrand is a scalar, so that seems reasonable. Well, same thing here, frankly. We call this a scalar surface integral because that's a scalar and that's a scalar. And why make the distinction at all? Well, you can probably see this coming, just like with line integrals. We are going to very soon, as in later today, talk about a different kind of a surface integral where these are not scalars, where instead they are vectors. And so coming up real soon, later today, we will be seeing vector surface integrals. But for now, just scalar surface integrals as we have here. Okay, how do we compute these things? Well, frankly, we've already got a lot of that work done. We're going to pull back through a parameterization. Again, familiar idea. Look back when we were looking at curves. We had a parameterization of the curve, and we pull back through that parameterization. And again, when we were doing curve integrals, all these details were already worked out. We didn't realize as we approached that we already had this all done, but in fact we had it all done. So this is again a very familiar situation that we're looking at. All of this setup work concerning this parameterization is done. The stretching factor, right? Already computed. How convenient, right? And so all we have to do is just kind of write down what we effectively already know. If you're doing a scalar surface integral, well, ds is stretching factor times ds dt. And we're in business. This is the pullback integral in the parameter space domain, ds dt. Okay. Everybody okay with that? By the way, I'm a big believer in noticing the analogy to scalar line integrals. Very strong comparison there. It's not exact, of course. Different context, geometrically appropriately different, but very, very analogous. Okay, now there is a little bit of a concern. This integral right here is about a surface. The surface does not actually need to be parameterized for this to be defined. Right? This is a chop it up, add it up on a surface. When we say we're going to compute it with something that comes from a parameterization, the concern is, wait a minute, how do I know that this expression over here gives the same answer for every parameterization? I mean, it's better because this purple integral over here has never even heard of a parameterization. This is definitely independent of the parameterization. So how do we know that this thing is? I mean, I'm concerned because of the fact I can see the parameterization in it. And when you can see it, then there's a definite concern that it might actually be doing something. Right? So good news, and we're not going to talk about the details up here, but this expression here is independent of the parameterization. Parameterize however you want. It won't make any difference. Now, this is a fact that the book spends some time developing. That's very appropriate for a class that's at a higher level than Math 219. For Math 219, it's a proofier and more rigor-oriented than Math 219 is. We're a little bit more sort of computationally intuition, geometric, this kind of thing. Okay. So y'all don't have to worry about why this is true, but I do think it's still important to be aware of the fact that it is true. Okay. All right. So, example. Suppose I want to compute. Well, let me say that differently. Suppose we have a mass distributed across the upper unit hemisphere, and the mass is distributed in such a way that the density goes by this formula. So, the higher you go up, the more mass per unit area there is on the surface. And I want to compute the mass. Okay, but I also want to compute the location of the center of mass. Oh, I also want to compute the moment of inertia around it. I want to compute a bunch of things all on this same distribution of mass on this same surface. All right, now again, this might look familiar. This is the first example that we did with scalar line integrals. Right? I defined a scenario and a bunch of different things you can compute, all with largely the same calculations because they're all being done on the same surface, using the same parameterization, with the same density. So a lot of stuff is the same, right? So likewise here with this question where I've got several different things that I want to compute, I'm going to do basically parallel calculations because they're all morally the same calculation, really. Okay, they're all going to follow this formula here, for which you notice we need to know the stretching factor. So let's go ahead and get that stretching factor computed. Here's my parameterization. By the way, think that one through. Make sure you're good with this. This is the spherical graph parameterization from rho equals 1, right? One of our parameterization tricks. And you can compute various partials, take the cross product, compute the magnitude, and what you find is that your stretching factor ends up being very conveniently just sine phi. That's very nice. How we doing? Everybody with me on that? This might even look familiar. I believe we did this calculation last time, actually. Okay. Alrighty, so the rest of these calculations is very, very similar. So first of all, the whole is the sum of the parts. Chop it up, add it up. All right. Mass is mass per unit area times area. Right? We've done things analogous to that a million times. Here's our stretching factor formula. Output area is proportional to input area by way of that stretching factor, magnitude of capital N. And of course, by the way, we just got through computing the magnitude of capital N. Here it is, our stretching factor, right there. Let's see here. We've got, here it is, density is Z. So let's plug in density is Z right there. And one last little detail, we have to ask ourselves, what is this Z here? And make sure to recall when you're plugging in, all of what you plug in comes directly out of the parameterization itself. And specifically, this is X, and this is Y, and this is Z. Right there. Right? So Z is cosine phi. Straight out of the parameterization. Everybody good? All right. Last little detail, you got to think about how this parameterization, how does this give you the upper unit hemisphere, specifically for what range of values? And I think it's a believable claim that theta goes from 0 to 2 pi, and phi, again, it's just the upper unit hemisphere, so phi goes from 0 to pi over 2. Everybody comfortable with that? Okay, so the other computations, a lot of it's exactly the same. Sure, there's different details. There, for example, is an extra factor of X in there that you got to carry through. And then, wait a second, what is X? How do I plug in for that X? Well, X is right there. So it's like that. Everything else is the same. A lot of analogies in these computations. Okay. Okay, how we doing? Everybody's happy. Okay, so now we're going to compute a different thing now. We're going to use the surface integral strategy to compute, we're going to try to compute flux. And a quick reminder, flux, here's the formula for flux. Check chapter 3 for some reminder discussions of, what that means. But the short version, I'll remind you here, flux, what it means depends on what the vector field is. If your vector field is representing the velocity of your fluid, then flux gives you volume per unit time moving through that piece of surface. On the other hand, if your vector field is density times velocity, which makes a lot of sense in some contexts, right? It really does. In that case, flux gives you quantity or mass of fluid per unit time passing through your surface. So, different applications in different cases. In all cases, this expression called flux is interesting for, well, again, one reason or another appropriate to the application. Now, I want to emphasize, this is if your vector field represents fluid flow in some way or another. Turns out, and we haven't seen any examples of this yet particularly, but flux is also interesting even in other cases, even if your vector field represents, electric forces, gravitational force, the gravitational field, electric field. It's not exactly a flow of a fluid through a surface in that case, and yet flux will still mean something useful and natural and important, and we'll get to that eventually. Okay, so the thing is, this formula assumes certain nice things about our circumstance, namely the vector field is constant and the surface is flat. All right, now you may be thinking to yourself, this all sounds vaguely familiar, and it is. Look at this discussion that we did when we were talking about work. We were going to try to use the idea of a scalar line integral to compute work. Work was computed with a dot product formula that made certain assumptions. The vector field is constant. The domain is straight, aka flat, right? So we are in a very similar circumstance here. Right now we are looking at a different thing. It's flux through the surface as opposed to work as we move along the surface. So it's geometrically different. It's also two-dimensional instead of one-dimensional. I mean, it's definitely different, right? Geometrically different circumstance. The algebra is correspondingly different, appropriate to the circumstance. But a lot of similarities. So what we did is we said, well, okay, still we're going to chop everything up into little pieces, and then on each little piece, we're going to write down our formula, and having written down the formula on that little piece, we end up with a new kind of integral that we have to, in this case, we had to call this a vector line integral because it is a fundamentally different structure that we end up with. I got a sneeze coming on here, I'm sorry. I think I talked myself out of it. Okay, so we're going to do basically the same thing here. We are going to take our surface, chop it up into little pieces. Here's my whole surface. I'm going to chop it up into little pieces and say, hey, let's add up over all these little pieces. In other words, let's just do a surface integral. We've already talked about how to do a surface integral. On each one of these little pieces, well, the piece is approximately flat, and not perfectly, of course, right? But in the limit, it's going to get smaller and smaller and flatter, and this will get more and more appropriate. And in Math 219, I'm just going to wave my hands and say, in the limit for nice surfaces, this is fine, right? As we have for every other kind of integral we've done. Ditto, the vector field. Not exactly constant, but over small little pieces, especially in the limit as these pieces get smaller and smaller. The vector field doesn't have enough time to change very much, and so it's approximately constant. Okay. We then write down, I'll come back to the stuff I just skipped over momentarily. We look at our circumstance now. We have a, call it, flat little piece of surface area. We have a, close enough, constant vector field on which we can just write down our old formula. This is just the basic formula for flux through a surface. F dot n times the area. Area is ds. And then we add up over the entire surface. d phi being computed by this. I rewrite like that. And this is what we're going to call a vector surface integral. I'll get to this notation here in a minute. Okay, now I glossed over an important little detail, and that is the business about orientation. Let me go back to the curves circumstance and remind you that orientation really matters. If you're interested in computing the amount of work that it takes to move along a curve, it really depends on which direction you're going. If that's a hiking trail, well, how much work does it take to hike a trail? It depends. You going uphill or downhill? Uphill's harder, right? At least in terms of the work computation. So we can't really talk about work along a curve, a mere curve. It's ambiguous. It could go either way. You're going to get different answers, clearly. We need a new thing. We need something called an oriented curve. And an oriented curve has an attached sense of direction. Which direction do you mean? Not just the curve itself, but then paired with the notion of what the direction is that you're going. And we describe the direction by way of tangent vectors along the curve or things like that. Okay, well, Same deal here. If you're interested in flux through this surface, flux which direction? If somebody were to tell you the flux through this surface is 5, does that mean it's up? Going up by a quantity of 5, or is it maybe that's down? Right? They're clearly different things. If the vector fields if the flow is going the other direction, we're going to get the negative answer of what we should have gotten, or what we would have otherwise gotten. How do you keep track of that? Right? We need some sort of an indication of what the right direction is, not along the curve. Right? We need a notion of what is the right direction through the surface. What is the positive? What are we going to call the positive direction through the surface? And that attached notion of which is the positive direction through the surface is what we call an orientation. So when we're talking about computing flux through a surface, it's not good enough to just have a surface. We need an oriented surface. Is that cool? Everybody happy with that? All right. Okay. All right. So that orientation, you notice, factors in to the calculation, right? So this orientation, that tells me what my little unit normal vector is there. And if you were to phrase a question with this as the orientation of my piece of surface, then great, you use that vector, etc., and calculate away. If you were to change the question to what is the flux downward through this surface, well, then you'd have a normal vector that's pointing exactly the opposite direction, and you'd get a minus sign on here. Okay. All right. Okay, so let's talk about this notation here. What is that ds vector? You can, of course, kind of see from the way this is written that this is what it is. It is the normal vector, the unit normal vector times the ds scalar. Why would we combine those things into one single, what we call surface differential? This ds vector. A couple different ways to think about it. One is the normal vector is a property of the surface. This little piece of area is a property of the surface. Together, both of these things are describing a piece of the surface. They're totally independent of the vector field. The vector field that exists independent of the surface, right? The surface exists independent of the vector field. The vector field is a separate thing. Right? So if only for that, I think it makes sense to isolate stuff that's relevant to the domain as being what your differential is. And what is not relevant to the domain is your integrand that goes on the inside there. So it's kind of natural in that sense. Let me point out further, this is not our first time to do this. Let's go back to when we were computing scalar line integrals. Right? And let's see here. I guess this is visible enough. What is our dx? Or I'll do it right here. What is our dx vector? Well, our dx vector could be thought of different ways, one of which is a unit vector describing my orientation on the curve combined with a scalar differential representing the size of the piece of curve. Right? So, unit vector representing the orientation, scalar differential representing the size. Notice that's exactly what's going on over here. That's exactly what this is that I'm calling the ds vector. Unit vector representing the orientation. This time the orientation through the surface, not along the curve, but through the surface. So orientation combined with a scalar differential representing size. This time the size, namely the area of a piece of the surface, not the length of a piece of the curve. So very strongly analogous to this existing dx vector notation that we have from long ago. And that makes this natural as well. So we have here basically, I'm going to say we have two different notations for how to compute flux. My personal favorite is this one here. I think that one, let's see, why do I like it? For one thing, it requires the fewest pen strokes, right? That's got to count for something. That's nice. The other thing is, as I've already pointed out, I think it makes loads of sense to have your differential tell you about what you need to know about about your domain, and to have your integrand be the thing that's not the domain. All participants in the calculation that are not part of the domain. So it's more natural to me. And if you look by comparison at this right here, what you would call your integrand, seemingly, part of your integrand is actually kind of, I would say, should be part of your differential. It describes the domain. I just think that's awkward. Okay, you're going to see both of these notations. Be aware. You're welcome to have a preference, of course, as to which one you like. Heads up, in my course, you're going to see this one here a lot. Because again, as I just described, I think it makes more sense. It's more natural. Fewer pen strokes. But in other contexts, you might see that instead. All right, how are we doing? Everybody's with me? All right. So, again, reminder, we already have all of this set up. This is nothing new in what I've got circled here. This is all old news. We've got a surface. We're parameterizing the little pieces of area relate to those little pieces of area. We've got notation set up. We know our stretching factor. Our stretching factor is the magnitude of capital N. Capital N computed by that formula. But this is all established. With that established, let's try to find another way that we can represent flux. This right here being, of course, exactly what we wrote down up here. This is literally a copy-paste. It's what we've already got written down there. So here's what I'm going to do. First thing I'm going to do is write my formula for the ds scalar. Right? We already knew that. ds scalar is magnitude of capital N times ds dt. And now begins the slick move. And the very first thing I have to do is put an asterisk on this. So I'm about to say that that's equal to that. This is a little bit of a math crime. I'm confessing in advance, self-defense, right? I don't want anyone to think that I'm doing this wrong. I know that what I'm about to tell you is wrong. I'm doing it on purpose. The reason I'm doing it on purpose is, frankly, we've got enough going on as it is, and I don't want to distract the matter and complicate things further. Right now, I want to get a formula down. I want to get a one in the win column. Let's get a victory under our belts, having computed one of these things. And after that, I'm going to come back and address the further complication that I am currently going to sweep under the rug. Right, so we will get to it, but let's not juggle too many balls all at once. It's not a good way to keep track of things. Okay, so with that confession out of the way, let's think about this product. This is a unit vector in the direction of capital N. This is the magnitude of capital N. Keep in mind, a vector is characterized by its direction and its magnitude. This product, therefore, is pointing in the direction and has the same magnitude of capital N. So it's capital N. Now, I've already confessed that I've made a math crime here. What I just said is faulty. And if you want to think about what that fault is and the mistake that I'm making here, go ahead. I encourage, looking for that. But don't worry. You don't have to worry about it right now. For the moment, let's just run with this. By the way, for whatever it's worth, this answer here is close enough to right that we are going to be able to get good stuff done with this. This is not wrong in the sense that it should be thrown away. It's just there needs to be an asterisk. We'll come back to that. Okay. So here's our, what I'm going to call our parametrized formula for vector surface integrals. So arguably most easily motivated by this formula, most easily represented by this formula, and arguably most easily computed by this formula right here. All right, let's do one. Let's get a win under our belts. Okay, here's a vector field. I've got a surface here, namely the portion of a certain graph that's sitting above a certain square in the XY plane, and I want to compute the flux. Okay, how do we compute flux? Well, we know how to compute flux. It's this formula that we just got through writing down. So let's put that on the page. Notice, in order to be able to compute this, I'm going to need my capital N vector. Notice, in order to compute the capital N vector, I need these partials. Notice, in order to compute those partials, I need a parameterization in the first place. Right? So let's start at the beginning. Let's actually start by taking this surface, z equals x squared plus y squared. We parameterize the graph parameterization here. You'll notice that I'm using, right, my personal favorite parameterization method. This is a graph. Makes it really easy to parameterize with that graph parameterization trick. And then easy partials, easy cross product, and don't even have to compute the magnitude. Notice, by the way, it's capital N itself is the thing. Very conveniently, no magnitude necessary. Okay, and with that noted, let's see here. The vector field is, there it is, which is this. Oh, now wait a second. What happened here? Why is it not z squared that I've written down as my first entry? Well, in fact, I have. Keep in mind, x, y, and z are given by the parameterization. This here is x. Right? So x is S. Everybody see what happened there? Okay. And Y is T, etc. But now let's look at Z. That Z is S squared plus T squared. Ooh, doggone it. Let's try that again. Z is S squared plus T squared. Watch out for your squares. It's really easy to mess this up. It's you know, S squared plus T squared, and then you see a Z squared up here. It'd be really easy to accidentally just transcribe this as just S squared plus T squared, but don't forget the Z itself is squared. So it's S squared plus T squared squared. So anyway, I'm sure y'all can follow the algebra there, but my point here is to be careful. It's really easy to oops in situations like that. Everybody happy? Okay. Then, of course, our N vector, we just computed here. That's just a recopy. And we're in business. One other thing we should talk about. Let's see, we're looking at just a portion of the surface, specifically the portion sitting over the unit square. That means we're looking at the portion of this surface where x and y range between 0 and 1. Don't forget that x and y are s and t. So that means that s and t range between 0 and 1 also. Is everybody happy with that? Okay, cool. And let's see here. Now, let me get to what I did wrong. Right? What is the issue here? Why is this asterisk worthy? And it comes from asking this question here: does the parameterization matter? Now, when we were doing scalar surface integrals, doesn't matter. Scalar surface integrals, parameterize however you like, doesn't matter. It's all good. It's fine. No issue. They just always give you the same answer as well. Of course they should. With a vector surface integral, there is an issue. Now, let me give a hint as to what that issue is. Again, I'm a big believer in observing similarities and analogies when they happen. When we were thinking about vector line integrals, you have to get the orientation right. Right? The orientation really matters. If you parameterize the same curve but with opposite orientations, you will not get the same answer. The parameterization matters in that sense. In the sense that, plus or minus, depending on whether you orient correctly or incorrectly. Okay. So, good news. That is exactly the issue here. It just boils down to orientation, and only orientation matters. But here's what I mean by orientation. So let me just remind you. When you're computing a flux, the way the question comes at you is there is a surface that you're asked to compute the flux through, and furthermore, there is what we call an orientation. We talked about what an orientation is. It's described by the orientation unit normal, which is just, it's a unit normal vector for that surface pointing in, whichever direction is to be viewed as the positive direction through the surface. It's arbitrary. Perfectly reasonable to ask, for example, given this surface, I want to keep track of the flow of the fluid down. I want positive to mean flow of fluid downward through the surface. That would be a perfectly reasonable thing to talk about, right? In which case your unit normal vector would be that one. But you might want to talk about flux upward through the surface, in which case that would be your orientation unit normal. The point is, it's part of the question. It's a choice of the question asker. Right? It's part of the question. Now that said, when you try to answer the question, you parameterize, which is going to give you your various partials, which you can cross to get your capital N vector, which you can then normalize, which will give you what we've called the parameterized unit normal. Where in the process of parameterizing did we plan and arrange for this unit normal to point in the same direction as whichever one the surface was defined as being its unit normal? And answer, nowhere, typically. Typically, when you're parameterizing something, you don't parameterize in a direction because it's a surface. It doesn't have a direction. It's very, very hard to see as you're writing down a parameterization which way is the normal vector going to point. It's really hard to tell. Right? So, as it stands, it's a coin flip as to whether you will have parameterized the correct direction or whether inadvertently, hardly blame yourself, you might have parameterized backwards. Okay. All right. So, this is where my crime was. Let's look back at this algebra. Here was my asterisk. I made the claim that is equal to this because, same direction, same magnitude, blah, blah, blah. I deliberately swept it under the rug, though, that this right here, this was the orientation unit normal. We compute f dot n, where n is what comes in the statement of the question as defining what is the proper direction through the surface. But this thing down here, right, when I claim that capital N is equal to that, no, capital N is equal to, I'll say it points in the direction of the parameterized unit normal. So, what capital N is actually equal to depends on something that 50-50 is pointing the exact opposite direction of the direction that it should. So, that's the problem. Okay. All right. So, how do we deal with this? If it turns out that I've gotten the orientation wrong, do I need to reparameterize and start over? No. Good news. If you're wrong, then you're wrong by a factor of -1. And you may recall, and we did this back in when we were doing line integrals, right? If you have parameterized the wrong way, just say so, right? And say, yeah, look, this curve is going the wrong direction of what I want, so I'm just going to insert a minus sign here, and then and go ahead and calculate as I've previously calculated, and take advantage of the fact that I know that going the wrong direction amounts to only a minus sign. And so we can do the same thing here. If you have parameterized upside down, and I'll tell you next time how to tell whether you've parameterized right side up or upside down. You don't need to re-parameterize. Just throw in a factor of -1 in the appropriate place and put a little comment that says, whoopsie, parameterized backwards, here's my -1, and then go on with your calculation. All right, good place to stop it, and we will pick up here next time. See y'all later. Have a good one.